Okay, so this is going to be the last video, I promise, of break. So the final wave property that we need to discuss is the property of refraction. So remember, diffraction was how waves tend to spread out as they travel, and as a result of spreading out, they move around and through things. Longer wavelengths spread out more, so they move around and through things easier. I guess easier maybe isn't the best word, but um, they spread out, they diffract more. Refraction, however, is also a property of light, but it has to do with when well, a property of any wave has to do with a change in medium. So remember we said early on with waves that the speed of a wave is totally dependent on the medium. Well, now here's where that really matters because as waves travel from one medium into a different medium, the speed changes. And as a result of that change in speed, we also get a change in direction. So this whole idea of changing speeds from one medium to another, and as a result, a change in direction or the bending of light is called refraction. So not only light refracts, but once again, it's a lot easier. You see this picture of the block with the laser. We're going to be replicating some experimental work similar to that. It's very easy to observe, it's very easy to measure, and it's very easy to test the laws of refraction with simple experiments. Sound waves do it too, right? Sound will bend if there's a sudden change in temperature, for example. Sound waves will tend to bend. This is why it's not. It seems like when you're standing at the edge of the water, seems like you can hear a greater distance, maybe across the lake. That is totally true because the temperature difference above the water, temperature of water is highly constant because of the high specific heat capacity of water. So air right above water tends to always be cooler than air above it. So sound waves will tend to bend back down towards the lake, enabling you to kind of collect more of those sound waves and hear at greater distance. So let's talk. We're going to stick with light though. So let's talk with light and stick with it. So it makes sense that when light travels from let's say, from air into water, that it would slow down. But it doesn't necessarily make a lot of sense why it would change directions. Well, remember, refraction is not a wave-specific phenomenon. Particles do it too. So if we imagine these are two very common analogies, I think the one on the right is this toy car works a little better. If a toy car changes from one type of flooring to another, you can see that the right wheel is going to hit the carpeting, I guess that is, um, before the left wheel does, causing the right wheel to slow down, and the left wheel is going to continue on at the same speed until it hits the carpet, causing the path of the car to change. That's refraction. That's essentially what light does too. Instead of a toy car, if we imagine wave fronts traveling, right? When this side of the wave front hits the now this wouldn't be carpet, of course, it would be something like glass compared to air. It's going to cause it to slow down the same way. Then, um, soldiers marching in formation, right? If they are to keep their formation, those that go from concrete to sand or the swamp are going to march a little bit slower. So the other ones on the outside edge are going to be moving faster to try to stay in formation. Um, Therefore, it's going to cause the entire um, whatever their troop of soldiers to change their direction. That'd be a good example analogy for refraction as well. So let's talk about how do we identify materials based on how much light's going to slow down. We use this term called the index of refraction, and we measure it. It's just abbreviated with an N, index of refraction. There are no units as we see it. It's simply a ratio. The index of refraction is a ratio of the speed of light in a vacuum, which is this 300 million meters per second, to the speed of light in that particular material. So we can write this in equation form as simply n equals c over v. It's a ratio. It has no units. It's meters per second over meters per second. So an index of refraction, if you think about it, can never be less than 1 because the speed of light in a vacuum is the absolute greatest speed that anything can attain. So c over the greatest speed v could ever be would be c, which would be very close to 1. So The index of refraction for air, for example, we make the assumption that light travels just about as fast in air as it does in a vacuum. So we say that the index of refraction of air is about 1. But for example, another common material that we use is water. The index of refraction of water is 1.33. So that means the ratio of the speed of light to the speed of light in water is 1.33. So we can calculate that. So you calculate that. How fast would light travel? When I say light, I mean all electromagnetic radiation, even though we basically use visible light. How fast would light travel in water? Well, 1.33 equals 300 million divided by V, which is what we want. So V equals 300 million divided by 1.33, which gives somewhere, I guess, around 2 point something times 10 to the 8th meters per second. So everything, any material, V has to be less than 300 million. So you know you're making a mistake if you get something greater. So an index of refraction, let's use an easy one, of 2 would mean that light travels at exactly 1/2 the speed of light in a vacuum in that material. So the index of refraction is going to be how we classify different kinds of materials and use it then to calculate how much will light bend. The greater the index of refraction, the more, just like the thicker the shag carpet, the more that car is going to slow down when it hits it, and the more the car's direction is going to change. So we'll skim through this one, but diamond, for example, has a very high index of refraction. This is what makes it very rare, very desirable. I don't know about valuable, but it makes it very desirable, which then makes it very valuable. So the fact that diamond has a high index of refraction means that light slows down quite a bit. It's 2.42 times slower in diamond than it is in air. This is what makes diamonds so sparkly. And when we get to when light bends, it bends so much in diamond that it gets trapped depending on how it's cut. The cut of the diamond is very important. Light gets trapped inside of there and it gets reflected back, and you see it. We call it the brilliance, what makes it very shiny and sparkly. So first of all, let's talk about how do we set these types of things up. We first of all have a boundary from one material and another. So we're going to call this material A and material B. This could be, let's go over to here. This could be air and water, or air and glass, or water and glass and a different kind of glass, diamond and water, whatever. It could be any two things. But what we need to know about those two things are, what is the index of refraction? So for example, the index of refraction of air would be 1, and the index of refraction of water would be 1.33. So it's important that we know that it's going from a lower index of refraction to a higher index of refraction. So we have two rays that we need to be able to define. We have the incident ray, right? That's the ray of light that hits the boundary from air to water. And then we have the refracted ray. That's the ray of light then that bends or changes directions. As a result, we have the angle that the incident ray, and this is very important that we know that when we classify angles with optics, it's always with respect to the normal, or the line perpendicular to the boundary. So, if you were to classify the angle over here, I mean, technically that would be wrong, but when you try to calculate, no one's going to know what you're talking about because there's a convention here. We always report angles to the normal. So we have an angle of incidence and an angle of refraction. The index and the angles are related by a very simple calculation called Snell's law. So Snell's law tells us that the index of the incident material times the sine of the incident angle has to be the same as the index of the refracted, or the material that the light goes into, times sine of the refracted angle. So we can make a lot of predictions then. For example, let's say that this is a boundary between, let's use air again, right? So we know that air is n equals 1. and we'll use water again, and n equals 1.33. So let's say we have an incident ray of light, and let's say there it is. It hits right there. So the first thing that we want to be able to do is say that let's extend it on both sides, and let's make that, typically want to make that a dotted line so we can, no, it's not a ray, it's just a line. So there's our n, right? That's our normal line. So that means we have the angle of incidence right there. So my question then is, how can we predict what the angle of refraction is going to be? We have a couple of choices. So if the ray didn't refract at all, I guess it looks something. Okay, so maybe down a little bit. Okay, so there's my unrefracted ray. Now that would be true if it went from air to air, or the index was so similar that it wouldn't refract very much. So is the angle of incidence going to get bigger or smaller? In other words, is it going to bend away from the normal or towards the normal? Well, we use Snell's law to figure that out. Snell's law says that Ni sine theta I has to be equal to Nr sine theta R, which means if my index of refraction is greater on this side, then my angle must be smaller on this side. So anytime we go from n, a smaller n to a larger n, in other words, what we're saying is that light is slowing down, then the ray will always bend towards, whoops, I don't want to do that, I want to bend it towards the normal. So my angle of refraction has to be smaller than my angle of incidence because my index of refraction is larger on the refracted side. So we use Snell's law to calculate these types of things. And Snell's law in refraction is kind of a neat phenomenon. Unfortunately, we can't spend a lot of time on it, but it's not particularly difficult if we know how to use Snell's law to both calculate and make predictions about which way the light is going to travel. In class, we'll spend a little bit of time on some of the finer details, like, what happens if I have different colors of light? Do all colors bend the same? Well, yeah, actually, the answer is no. That the amount of refraction is also wavelength dependent. So we'll get into that a little bit as well. We also will talk about that if we go from, let's say we go the other way with it. Let's use my little app thing here. So here in this case, I can change my angle. And you can see that if I go from a smaller, in this case I have n equals 1 and n equals 1.5. 1.5 is probably some kind of glass. Yeah, it says glass. So as I get bigger and bigger and bigger and bigger and bigger and bigger and bigger, my angle of incidence is always bigger than my angle of refraction, but both angles get bigger and bigger and bigger. But the angle theta on the top is always bigger than the bottom. So what that means is I'm eventually going to hit 90 degrees. You also notice the reflected angle up here too. Remember the law of reflection if you've done your optics assignment? We always get some reflection at the boundary too. The greater the angle, the more the light is reflected. But eventually I have a limit. Now look what happens if I reverse it. So now I'm going from n equals 1.5 on the bottom to n equals 1 on top. So now, as my angle, let's start at 90, as my angle of incidence increases, the refracted ray is bending away from the normal. So there's going to be some angle at which no longer, you see that refracted ray is getting closer and closer to the boundary. So at that point, no light then escapes. We call that total internal reflection. And total internal reflection occurs when the angle of incidence, we call it the critical angle, creates an angle of refraction of 90 degrees. So Snell's law says that n sine theta equals nr sine theta. Now, if you think about the math here, this is only possible if n on the incident side is greater because we want the theta on the refracted side to be greater. So over here, we call this the critical angle, right, for that particular material equals nr, and then what's sine 90 is just 1. So we have this type of relationship. If this side um, is air, then we could also say the refracted side that n equals 1 as well. We could say ni sine theta, and it commonly is air, by the way. And it would just be ni sine theta equals 1, and I can solve for the critical angle. So all materials have an index of refraction. They also have a critical angle, which means light cannot escape if it's beyond that particular angle. So those problems are also in your web assign. Get a quick head start on that. I'm at 16 minutes here, so I got to wrap this up. So refraction and diffraction are the two topics we have to finish up in just the first day back. So do a little work for me before class, and we'll make class more useful. Enjoy the rest of your break.